Example 7. Let's look at an exercise where we are asked to determine which of the two possible complexes will be formed when there are two possible central atoms and one ligand in the solution. There are two options, Y4+ with zinc or with iron. The way to solve the exercise is to multiply the reaction by the smaller constant but -1, that is, to reverse the reaction. Then both should be added. By doing this, we obtain a chemical reaction where the free ligand can be eliminated from both sides. Finally, the quotient between both reactions should be done, the smaller one on the denominator, to find out how different the two constants are. The formation of the iron complex is favoured by 10 to 8 times over the zinc complex. Exercise 8 is similar. Here we have a solution with a diamond-silver complex, and we add cyanide anion which can act as a ligand for silver. Will the metal join with a new ligand or keep its current structure? Let's write the two possible coordination complex formation reactions. By doing this, we can see that the complex obtained after adding cyanide ions to the solution is the cyano-silver coordination complex. The cyano complex is favoured by 13.9 times over the ammonia complex. Here we are considering similar concentrations of ligands. Now that we have studied precipitation and complexes separately, we're going to see examples where these two topics come together. In this exercise, we have a solution with precipitated silver iodide, and we want to know how the solubility changes when adding ammonia. When adding ammonia, the silver cations can bond to it and form a coordination complex. Therefore, free silver cations are reduced in the solution. The solubility equilibrium shifts towards the right according to Le Chatelier principle to balance the diminishing concentration. In the next exercise, we're going to see how the solubility changes with pH. We have two different possible reactions. The solid chromium hydroxide solubilizes in aqueous solution to obtain chromium 3+ and 3 hydroxides. Each of the chromium cations can react with different amounts of hydroxide anions and form different coordination complexes. 3 of the possible complexes formed have charge and 1 is neutral, 3-hydroxychromium 3. In this one, we write aqueous to distinguish it from the initial solid chromium hydroxide, which is precipitated. We should write the mass balance of the chromium as it is the central atom in the coordination complex is formed. In the mass balance, all the species where chromium can be present should appear. So, at this point, we know the expression of the solubility constant KSO and its value. To simplify and shorten the exercise, beta 1 and beta 2 are ignored, also because they are much smaller than the other betas 3 and 4. Working with betas, we have more unknown values than equations. However, working with KSN, we can solve the system. In a previous slide, we saw the existing relationship between these two. The value of beta 3 and its constant is known, as well as beta 4. What happens if equations 1 and 2 are added? The chromium 3 and hydroxides can be eliminated, and we have the change from solid chromium hydroxide to aqueous coordination complexes. The constant is then Ks3, which is the product of the solubility constant and beta 3. If we add equations 1 and 3, 3 of the 4 hydroxides are eliminated, and we are left with chromium hydroxide plus 1 hydroxide ion, which gives the tetrahydroxychromium 3 complex, with constant Ks4 being the solubility constant multiplied by beta 4. Let's suppose that we're interested in solubilizing the maximum amount of chromium-3. This is what we all call solubility. It is the maximum chromium-3 that is in solution. We want to know the relationship between the solubility of the chromium-3 and the pH of the solution. We have to do the mass balance of the metal. The total chromium-3 can be free or can form complexes in two different ways, two different coordination complexes, here and here. We can then replace each concentration with the value equilibriums named A, B and C. In the first case, we have the solubility constant divided by the hydroxide concentration to the power of 3. We substitute this in the free chromium concentration term, and then the other two, B and C, at each chromium species. The mass balance of the metal looks like this. If we represent the solubility using pH, we get a graph like this. The solubility decreases when increasing the pH due to the formation of hydroxide compounds, which are insoluble. These solids form due to the increase of hydroxide concentration at higher pH. There is a point of minimum solubility, and then the solubility increases again due to the formation of complexes with chromium and several hydroxides. The pH at the start of precipitation implies that the two addends on the right are negligible. In the total redissolution pH, all concentrations are as for the second complex. If we want to find this point of minimum solubility mathematically, we have to search for the point where there is a minimum in the mass balance. The derivative is equal to 0. Substituting the values and doing the derivative, we obtain a pH of 7.11.